Let me begin with the first assay. Antioxidants play an important role in terminating the oxidation process of free radical. The initial step starts when hydrogen atom is lost at double bond and forms a free radical in the presence of catalysts, heat, metal and light. The formed free radical reacts with oxygen to form peroxide free radical. This again breaks into a double bond to form another free radical. This reaction repeats several thousand times. Finally, the reaction comes to an end when the free radical reacts with antioxidants. Just a brief about assay. Assays measure the total capacity of antioxidants. Antioxidant assays are classified into two types. Can you guess them? Yes. It is hydrogen atom transfer, which is also called the HAT, and electron transfer, which is also called the ET. In HAT, antioxidants react with the substrate, that is the peroxyl radical, until it decomposes. Whereas in ET, the reduction of oxidants is measured by antioxidant capacity. This is observed by a change in color. The important parameter of ET is the ionizing potential of antioxidant, and for HAT, antioxidant action is based on bond dissociation enthalpy. Now talking about the FRAP. FRAP is an electron transfer based assay which was developed by Binzi and Stein in 1996. They first measured the plasma and later it was adapted to measure antioxidants in botanical. It has a redox potential of 0.7. What is the principle of FRAP? The principle of this FRAP is that they involve two components in the reaction mixture, antioxidant and oxidant, which is also called the probe. The probe abstracts an electron from antioxidant, causing color change of the probe. That is, the complex ferric ion TPTZ246-tri-2-pyridyl 135-triazine reduces on reacting with oxidant and forms a ferrous compound that binds with ligand to create an intense blue color. Thus, the absorbance can be measured to test the amount of ion reduced, and this can be correlated with the amount of antioxidant. FRAP assay is a non-specific redox-linked colorimetric assay related to the molar concentration of antioxidant. Okay, let's move on to the mechanism of FRAP. This is a simple assay wherein FRAP reagent is prepared using TPTZ, acetate buffer, and ferric chloride and water. At a low pH of 3.5, antioxidant reduces against oxidant, forming ferrous, which binds with the ligand to give a deep blue color. This change is observed at 593 nanometer. It is a quick reaction which occurs in less than. So, this is a reaction of electron transfer from antioxidant to ferric tripyridyl triazine to form the ferrous complex. Looking at the advantages and the disadvantages, they have got many advantages which are they are simple, inexpensive, speedy, automated, semi-automated and manual. The only drawback is that the assay cannot measure the antioxidant capacity of thiol group due to the low redox potential threshold. Thank you.
So the next assay is DPPH assay. DPPH assay or 2,2-diphenyl 1-picryl hydroxyl is a dark colored crystalline powder composed of stable free radical molecule. This is the structure of a DPPH molecule. It is an ET-based assay. It was first developed by Blois in 1958. It is used to determine the antioxidant activity by using a stable free radical. It is based on the measurement of the scavenging capacity of antioxidants. Now we'll study the mechanism of DPPH assay. The first step in the mechanism behind DPPH assay is the delocalization of the spare electron over the molecule as a whole. This delocalization gives rise to a deep violet color. The color changes from purple to yellow, followed by the formation of DPPH upon absorption of hydrogen atom. DPPH, when mixed with a substance that can donate a hydrogen atom, gives rise to reduced form with a loss of violet color. The general reaction to represent this mechanism is Z plus AH gives ZS plus A, where Z is the DPPH radical and AH is the donor molecule. We can see from this picture that the free radical is being changed into a non-radical. In the previous slides, we saw that the color gets changed from purple to yellow. why does this change in color occur? This change in color occurs because DPPH has a strong absorption band at 520 nanometers. Hence we get the violet color. It becomes pale yellow when it gets neutralized. We can see from the picture that the violet color is being changed into the yellow color. DPPH has certain advantages and disadvantages. Some of the advantages are it is an accurate, easy and economic method. It is rapid, simple, inexpensive and widely used. It measures the ability of compounds to act as free hydrogen donors. It measures the radical scavenging activity of fruits and vegetables. It is used for investigating antioxidant properties of wheat, grain, herbs, seed oils, etc. It is a convenient method for antioxidant assay of cysteines, glutathione, etc. Some of the disadvantages are it is sensitive to some Lewis bases and solvent types and also to oxygen. It is only soluble in organic solvents. The absorbance of DPPH assay in methanol and acetone decreases with light. Thank you.
Now we look into OREG assay. It is a hydrogen atom transfer or hat-based assay which uses molecular probes to measure the antioxidant activity of samples. It measures the antioxidant activity against free radicals on the basis of time-dependent decrease in the fluorescence intensity of the probe. The probes most widely used are beta-phycoerythrin and fluorescein. This assay measures the antioxidant capacity by measuring the ability of an antioxidant to minimize the damage done to the probe by free radicals, which is reflected in the integrity of fluorescence emission. Now, in simpler words, the fluorescence emission of beta-phycoerythrin is highly sensitive to the conformation and chemical integrity of the molecule. So a loss in the fluorescence would mean that the probe has been damaged. On the other hand, a decrease in the loss of fluorescence in the presence of an antioxidant would mean that there has been a decrease in the damage to the probe, and this gives us a measure of the antioxidant capacity against free radicals. In this assay, AAPH acts as a free radical generator, and in this reaction we can see that from one molecule of AAPH, two free peroxy radicals are formed. These free radicals attack the probe, which leads to a change in its conformation, which in turn leads to a loss in fluorescence. But in the presence of antioxidants, the free radicals get reduced. So the antioxidant competes with the probe to reduce the free radicals, and this inhibits the oxidation of the probe, and this minimizes the damage to the probe by free radicals. The level of antioxidant protection is measured by the area under the curve of the sample being tested as compared to that of the blank. Now this is a graph of the relative fluorescence intensity versus time, and this is the curve of the blank, and these are the curves of the antioxidant at various concentrations. Now we can notice that there is an initial lag phase in which the antioxidant is being consumed linearly with time, and this increases with the increase in the concentration of the antioxidant. Efficient antioxidants such as strologs produce a well-defined lag phase.
So the last is crocin bleaching assay. What is crocin bleaching assay? It is oxidation or bleaching of crocin by peroxyl radicals in the presence and absence of antioxidants. That is, it measures the inhibition capacity of antioxidants in bleaching of crocin. So what exactly is crocin? It is a carotenoid pigment naturally developed from saffron flower. It is responsible for the color of saffron threads, which you can see here. It is a HAT type assay. Materials required are crocin, the AAPH radical generator, antioxidant, and UV-vis spectrophotometer. Principle of crocin bleaching assay says that it is based on the competitive kinetic reaction between antioxidant and crocin with the peroxyl radicals in the presence of oxygen. This assay was first developed by Boers in 1984. So further, the inhibition of crocin bleaching by antioxidant was monitored at 443 nanometer for 10 minutes. What exactly results in crocin bleaching is the abstraction of hydrogen atoms to the polyene structure of crocin, that is the double bonded structure of crocin. So the reactions are consistent with the Stern-Volmer kinetic model, which you can see in this slide. Tubaro in 1998 used this for the analysis of plasma antioxidant capacity assay. This assay developed a graph which was the graph of antioxidant by crocin versus the absence and presence of antioxidant. The graph gave a straight line and the slope represented the relative peroxyl radical scavenging capacity. Also, online HPLC crocin bleaching assay system was developed by Bonta Kido in 2011. They used crocin as a substrate, AAPH as radical generator. HPLC CBA was tested for green tea extract, and this method was based on detection of antioxidants by their inhibitory effect on the bleaching of crocin. This assay did a comparative study between two chromatograms, that is UV chromatogram at 265 nanometer and CBA chromatogram at 440 nanometers. The main reason for the chromatogram was detection of EGCG, which is epigalactocatechin gallate. This forms the major potent antioxidant in green tea. In CBA chromatogram on the right hand side, we can see peak 7, which is a very elevated peak, and this peak represents the detection of EGCG. However, on the left hand side in UV chromatogram, peak 8 is elevated, which is the peak of epicatechin, which is also an antioxidant but not as potent as EGCG. Therefore, we can say that the sensitivity of CBA chromatogram is important in determining the crocin bleaching as compared to other online assays. Moving to the advantages of CBA, it uses peroxyl radicals and polyunsaturated substrate. It is simple to use and it detects the positive peaks in post-column chromatograph as we just saw. Disadvantages include that it is reduced sensitivity, it requires baseline correction, it requires high temperatures, the initial color of crocin is affected by the presence of other compounds, and lastly, crocin is a mixture of natural pigment which is subjected to a variability. Thank you.